Today we'll be solving trigonometric equations. To do so, we're going to use standard algebraic techniques such as collecting like terms and factoring, with the primary goal to isolate the trig function involved in the equation. So as an example, I've got solve 2 times sine of x minus 1 equals 0. So the first thing I want to do is isolate that sine of x. So get that sine of x by itself. Let's begin by adding 1 to both sides. So this will give me 2 times sine of x is equal to 1. And so now let's divide both sides by 2. And I'll see here that sine of x equals 1/2. Then what I'll want to do is one of two things. I can either graph this like I've done, just in any graphing utility, graph sine of x, and then graph y equals 1/2. And what you can see are the intersections of those two. So the sine is going to be a wave, and then y equals 1/2 will just be this horizontal dashed line here. And we see that this intersects multiple times, one of which is x equals pi over 6, and another is x equals 5 pi over 6. And what I see here is as this wave continues, these two spots will hit again at pi over 6 plus 2 pi, 5 pi over 6 plus 2 pi, and then over here, pi over 6 minus 2 pi, 5 pi over 6 minus 2 pi. So what does that actually mean? Well, if I look at my unit circle, this is asking where is sine of x equal to 1/2. So I'll find sine is my y value here. So where is that going to be 1/2? That's pi over 6 right here, and 5 pi over 6, which I saw here, pi over 6 and 5 pi over 6. Now this plus 2 pi and minus 2 pi are then saying that every time I go around a full circle, I come back to this spot again. And every time I go around a full circle, I come around to this spot again. And a full circle, as we have mentioned before, talking about unit circles, is 2 pi. So every time I go around 2 pi, pi over 6 plus 2 pi, pi over 6 plus 4 pi, pi over 6 plus 6 pi, I hit that spot again. So what this is really saying is I've got an infinite number of solutions here every time I hit that spot going around that circle, or every time that wave comes up and then goes back down, hitting those spots. So here's how I'm going to write that for an infinite number of solutions then. I'll say, since there are an infinite number of solutions, I write this as x equals pi over 6 plus 2n pi and x equals pi over 6. 5 pi over 6 plus 2n pi. And n here is just representing some integer telling us how many times around the circle am I going. Let's solve a couple more problems. This time we'll use quadratics. Find all solutions of 2 times sine squared of x minus sine of x minus 1 equals 0 in the interval 0 to 2 pi. So this part's important. 0 to 2 pi is telling me I don't want an infinite number of solutions. I just want around this first cycle, around this first circle. Now, you could factor this as it is. What might be helpful is to try and make this look a little bit easier. What I mean by that is, let's just say instead of sine squared of x and sine of x here, let's do something where we let's say we say let u equal sine of x. If we do that, then what we've got here is 2u squared minus u minus 1 equals 0. And this might just be a little bit easier to look at, work with, factor, because now I can see that I can use my AC kind of method for factoring. I'll say A equals 2 and C equals negative 1. So all the factors of 2 are just 1 times 2. And for negative 1, I've got 1 times negative 1, or I've got reverse that, negative 1 times positive 1. Well, let's see. If I put these two together, multiplying the outsides, I've got 1 times negative 1 would be negative 1. 2 times 1 would be positive 2. Those added together would be positive 1. That doesn't match the middle. So I know it's got to be 1, 2, and negative 1, 1. 1 times 1 is 1. 2 times negative 1 is negative 2. 1 plus negative 2 makes this negative 1. So this will factor 2. 1 and 2 means u and 2u. And then negative 1, positive 1, so minus 1 on the left, plus 1 on the right, equals 0. But remember that u is sine of x. So really this is sine of x minus 1 times 2 times sine of x plus 1 equals 0. And if these two are multiplied together and they equal 0, it implies that one of these must be 0. Now I don't know which one necessarily, so what I've got to do is split this up and say, what if the left one, what if sine of x minus 1 equals 0? Or what if 2 times sine of x plus 1 equals 0? What would happen in either of these cases? Well, let's solve for both. Add 1 here. And I'll get sine of x equals 1. Okay, what about over here? Subtract 1. Two times sine of x equals negative 1, and divide by 2. Sine of x equals negative 1/2. Lastly, once you're at this point, you're going to bring over your unit circle, and you're going to say, when is sine of x 1? Okay, sine of x is 1 at pi over 2, and that's it. So here, I'm just going to say x equals pi over 2. Okay, what about over here? Sine of x equals negative 1/2. So when is this negative 1/2? That's 7 pi over 6 and 11 pi over 6. So over here, I'll say x equals 7 pi over 6, and x equals 11 pi over 6. And I don't need to do the plus 2n pi here because it says the interval is from 0 to 2 pi. So I just want within that first circle. Okay, let's do one more. Solving trig equations using inverse functions. All right, so I've got find all solutions of secant squared of x minus 2 tangent of x equals 4. Now, this does not restrict me to 0 to 2 pi, so I want all the possible solutions. The first thing I want to do is see if I can get all of this into just a single type of trig function. Right now I've got secant and tangent here. So let's see, one of my Pythagorean identities is secant squared equals 1 plus tangent squared. So since secant squared equals 1 plus tangent squared as one of my Pythagorean identities, then I can replace secant squared here. Okay, so I say, from the Pythagorean identity, secant squared of x equals 1 plus tangent squared of x. Okay, then I can say that this secant squared is now 1 plus tangent squared. So let's replace that over here. 1 plus tangent squared of x. I still have minus 2 tangent of x equals 4. All right, let's clean this up. Let's reorder this a little bit. Let's just do tangent squared of x minus 2 tangent of x minus 1 equals 4. And let's bring everything over to one side. So I'll subtract 4 from both sides. Oh, this should actually be a plus 1. Okay, now let's subtract 4. So tangent squared of x minus 2 tangent of x minus 3 equals 0. And if you want to make this a little bit easier to work with, over to the side, you could say let u equal tangent of x. That way, this would be u squared minus 2u minus 3 equals 0. Then you could say a equals 1 here, c equals negative 3. Factors are 1 times 1, 1 times negative 3, or 3 times negative 1. All right, this is going to be 1, 1, 1, negative 3. 1 times negative 3 would be negative 3. 1 times 1 is 1. Add those together. That gives you the negative 2 here. So this will factor 2. One and 1 means u here, u here. 1 and negative 3 is plus 1 minus 3. And since earlier we said let u equal tangent of x, this is really tangent of x plus 1 times tangent of x minus 3 equals 0. Okay, then let's split this up. Since these are multiplied together and they equal 0, it implies that one of them, at least one of them, must be 0. So I'll say tangent of x over here plus 1 equals 0, or tangent of x minus 3 equals 0. Isolating tangent of x means we'll subtract 1 from both sides over here, and on this one, we're going to add 3 to both sides. Tangent of x equals -1, or tangent of x equals +3. So I'll bring back my unit circle, and I'll look on here and I'll say, is there at any point that tangent of x equals -1? So tangent's on the outside here. -1 is here at 3 pi over 4, and here at 7 pi over 4. So what I could say is x equals 3 pi over 4, x equals 7 pi over 4. But since it didn't limit me to just that first, didn't restrict me to that first circle, I want to say every time I go around the circle, I hit this point. So I'll say 3 pi over 4 plus 2n pi, and 7 pi over 4 plus 2n pi. Except there's a better way to write this. Instead of saying x is this and x is this, we can actually combine these together. What do I mean by that? Well, 3 pi over 4 and 7 pi over 4, notice that they are directly opposite of each other. Okay, 3 pi over 4 is right here, and right across the circle, exactly halfway across the circle, is 7 pi over 4. So instead of saying 3 pi over 4 plus a full circle gets me back to this spot, and 7 pi over 4 plus a full circle gets me back to this spot, I could simply say 3 pi over 4 plus half a circle will get me here, and then once I'm here, another half a circle will get back to 3 pi over 4. Another half a circle will get here, and then another half a circle will come back here, and so forth. So instead of saying 3 pi over 4 plus 2n pi and 7 pi over 4 plus 2n pi, I'm simply going to say this is the same as saying x equals 3 pi over 4 plus n pi, not the 2n pi. This is saying every time I go around half a circle, because half a circle is 1 pi, not 2 pi, I'm going to hit one of these two solutions. Okay, what about tangent of x equals 3? Well, that's not on here. So I'm simply going to say x equals the arctangent of 3 plus n pi. You'll have a lot of problems like these on your assignment. Just make sure to refer to your identities, your list of trig identities, and some tools from algebra to help you out in solving for these trigonometric equations.